Okay, so now you're probably guessing that now that we have these rules, with the horizontal bars, that we're now going to define an inductive predicate with, 6 introduction rules corresponding to these 6 horizontal bars. And that would be one approach to do things. So we could define the semantics of the wild language directly via hoare logic using such an inductive predicate. And then what we could do is we could show that this hoare logic is correct with respect to the either the big step or the small step semantics. So let's say the big step semantics is more natural here. We could show that the two coincide in some sense, right? That the two agree, that they specify the same semantics. So that would be one way to do things, but we're going to do it the other way because at some point we have to choose. So we're going to take what I call here the semantic approach. So we're going to define the truth value of a hoare triple in terms of the big step semantics, and derive all of the rules that we've seen as lemmas. All right, so let's start. So this is the definition of a hoare triple, and it just follows the English prose that we had over there. So it says, for all, so we have basically the triple P S Q, yeah, so this is the predicate we're defining. So partial hoare of P S Q. If, whenever you have, so this is for all S and T, these are states, right? So whenever you, let's start with S, whenever you're in a state that satisfies S, and you execute the program from S and you end up at T, then the final state T satisfies Q. This is what it says, right? So a few things, we could move the for all T further inside. That would also work. Maybe it's more intuitive, but sometimes it's nicer to have all the for alls up front and then the conditions afterwards. It just looks tidier somehow. But I mean, both work. And then the other thing to be very careful about is you have to parse this correctly, with the arrows and so on. So this is a very big, impressive arrow, and this is a small and tiny arrow. Nonetheless, the small arrow here has a lower precedence. So what we really are looking at is something that looks like this. All right, so we have 2 quantified variables, then we have 1 condition, 2 conditions, and then the conclusion. That's what we have. So be very careful here. The notations, I mean, the implication arrows in Lean are simply too short. So in other systems, in Isabelle, you have these huge arrows. And actually in Isabelle, this one means implication, right? Whereas this means nothing, it's tiny. Okay. And now we're going to introduce a notation as usual. Unfortunately, we cannot use exactly the same notation that we used informally because the curly braces also mean sets, right? You can form sets using them. So we're going to put a star as well next to the curly braces. So here's an example of a triple. All right. So this is the, we're going to define 6 rules, right? Introduction rules, I mean, there are also introduction rules, it's just that it's not an inductive predicate, but we're still going to call them intro. It's what, when you have a skip in a conclusion and you want, in the hoare triple, and you want to introduce it, as it's called, then you use skip intro. So you see P, that was the rule with the horizontal bar. And right, so what do? We're in this situation here. How do we prove something like this? Well, the key is to remember that this is just syntactic sugar. This tuple is just syntactic sugar for partial hoare here, right? So So maybe, I mean, let's try rewrite partial hoare. Right, and now we see what really happens, right? So we have for all st, then we have a condition, and then another condition. So this is what we intro here, right? And if you don't do the rewrite first, and you just write intros like this, nothing happens because intros is very timid. You have to tell it explicitly, you know, I want to intro this and that variable. You know, when you have a definition, it will not unfold definitions for you unless you force it to. It's kind of well, it's not timid. It's lazy if you like. So intros alone won't do it, but intros with explicit names works. But you have to know, okay, what comes where. So either you figure it out by yourself, or you first rewrite, then you do the intros, you do the rest of the proof, and then if you want, you can clean it up and say, oh, I don't need this step. If people want to understand better what happens there, they will do like I just did, right? You don't have to always put all the details in your proof scripts. So here what happened? Well, once we've done the intros, we have a new premise here which tells us that if you start at skip, if you start in S and you execute skip, you end up at T. And from this, from the fact that this is the big step semantics, you can do a cases on it, and it will, merge S and T. And then at this point you've won because you started with P of S and you ended up with P of T, but now they're merged. You have P of T and P of T. So it goes by assumption. And then you have, similar rule here for assign. Sequential composition is barely more complicated. So you can study these at home. If then else is, of course, you have two cases here. When you do the cases, the true case and the false case. But that's not, in here use HS, and here use HT, so use a different hypothesis. Here I should mention, you see the condition we write has a lambda. So if we follow the informal version, we would simply write this, P and B, but this doesn't work, you see, because P is a predicate on state, and B is also a predicate on state, and is it just takes propositions, not predicates as arguments. So you have to use a lambda, you extract the state, right, as a predicate, and then you call P of S and B of S. And you could always do that, right? So you could, in principle, here also say lambda S Q of S, but by eta reduction, you can just write Q, which is what we do. So that's the secret of that proof. Then we have the while here, which is, yeah, pretty boring ultimately. All right, so I have true. Here, I don't know why there's no case while false. We don't have to have it, but it would look more tidy. Okay. And we finally have the consequence rule. And for this one, we wrote the proof as a structured proof, right? It's been a while. And here you see this quite complicated term here. So again, we're not forcing you to write proofs like this, but this is a style that we decided to use here. Then you can prove some variants of the rule. So we have consequence left, which does only one of the two sides. So you just have one implication instead of two. So for example, this one here has P prime implies P, but it doesn't have a distinction between Q and Q prime. You just have Q and you have no implication. And then of course, analogously for consequence right in Q and Q prime. You also have these alternate versions that are that have linear patterns, which are easy to prove by using consequence and skip intro. And all of these proofs here are given in the term style. But again, you could easily just open the begin block and prove them the other way if you prefer. That's, that looks very tidy and compact, but to some people it's harder to read and harder to modify. So it's up to you. And yeah, so we have sec intro prime as well. And yeah, how does this work? One word. QR. Sec intro prime is just like sec intro, but it takes its two premises in reverse. So it takes this premise before, so HT before HS, whereas normally you take HS before HT. And you see the proof is very easy. But sometimes it comes in, it will come in handy later to have this, this order. And then we have a another while rule, which, well, let me look at it. What does it do differently, really? It, right. So this one distinguishes between the precondition and the invariant, right? So you start with P, and then you, you know, when you require that P implies I, and then you use I as your invariant, and you loop on I, and then at the end you want that I implies Q, and then you have Q. So you have a distinction between P, I, Q, instead of just you know, having P as we had before, or I as it should maybe be renamed. Okay, so that makes it more flexible. When we combine it with other rules, you know, things will fit better, because if we require syntactically that everything fits all the time, then that makes the rules less flexible, less pleasant to use. And here I I needed to prove some annoying proof obligation here, and I just couldn't be bothered because, well, basically it's HQ, but the condition, there's an N here, and here's an implication, the order is different. And then, you know, I tried my favorite CC and it failed, so I was a bit sad. I tried simp, you know, and that didn't work. And then I was like, let's try finish. And finish does it. Finish is quite powerful. It applies all sorts of techniques which are enumerated here, right? So it normalizes the connectives and quantifiers, it simplifies, it performs some congruence closure, instantiates some quantifiers heuristically, and either it fully succeeds or it fails. And, you know, I avoided introducing finish earlier because it would have destroyed some of the homework or the exercises. But of course, I'm sure some of you have managed to destroy them anyway by, you know, finding out about finish or tautology before they were introduced. And I mean, that's, you know, I cannot prevent all of that. I mean, I will have to write in every question, please do not do so and so. And, you know, I don't want to do that. You guys are adults, right? I mean, I guess, I don't know, I haven't checked your IDs. Okay. And then, well, there was this note here about assign. So we saw a backward version of assign, but there's also a forward version. So the backward one, you know, had the Q as the postcondition and had the modification of Q as the precondition. And whereas here we have P as the precondition and some modification of P as the postcondition. I am actually not going to cover it in class. It's not so important. But for those of you who are curious about, you know, why is assign backwards, or what would it look like forward, and why is there an asymmetry, and so on, this is explained in the Hitchhiker's Guide.